Welcome to Math Vision tutorial. My name is Moses. Kindly subscribe to my YouTube channel if you are new here, and don't forget to click on the notification bell to get notified whenever I drop a new video. So welcome to today's class. Today we shall be talking about the electric potential energy of a charge. Now, what is the electric potential energy of a charge? The electric potential energy U of a charge Q naught is simply the work done by an external force to bring the charge Q naught from infinity to a point Ra against an electric field E. The electric potential energy of a charge is simply the work required to bring that charge from infinity to a point against an electric field. Let's consider some illustration to understand the concept of electric potential energy. Now, let's consider the figure on the board. We have the big positive charge, which we denote as the capital Q, and we have the small positive charge, which we denote as the Q naught, which is the small Q naught. So the big positive charge, we call it the reference charge, and a small positive charge, we call it the test charge. We use a big positive charge and a small positive charge because we don't want the electric field of the small positive charge to have effect on the big positive charge. We only want the electric field of the big positive charge, which we call the reference charge. We are only in need of the field of the big positive charge. We want the electric field of the big positive charge to have effect on the small positive charge, but we don't want the electric field of the small positive charge to have effect on the big positive charge. That's the reason why we use a big positive charge and a small positive charge. The big positive charge is called the reference charge, and the small positive charge is called test charge. So now, let's consider myself to be an external force. I am trying to bring Q naught from infinity to a point Ra closer to the reference charge. Don't forget that the reference charge has created an electric field, a significant electric field, in such a way that when this small charge is coming closer to the big charge, the small charge will experience what we call electric force. I am the external force, bringing the test charge from infinity closer to the reference charge. In the process of bringing the test charge from infinity closer to the reference charge, I am forcing the charge on the reference charge because this charge is experiencing an electric force due to this reference charge. The charge will never want to move close to the reference charge. The small charge will never want to move close to the reference charge because of the electric force. So the charge will be trying to repel, but I am the one working on the charge to push the charge with force towards towards the reference charge. And in the process of forcing the test charge to the reference charge, a kind of energy is stored in the test charge. And the energy stored in the test charge is called the electric potential energy. Because I am the external force, I am doing some work on the charge. As I am doing some work on the charge to move the charge closer to the reference charge, I am storing an energy in the test charge. And the energy that I am storing in the test charge is called the electric potential energy. And don't forget that the electric force is produced by this reference charge. The electric force is produced by this reference charge, and the external force is me. So now, the least amount of force for me to push this test charge against the electric field, that is, for me to push this test charge against the electric field created by this reference charge, has to amount to the electric force. Let me come again. This test charge is experiencing an electric force due to this big positive charge. For me to be able to push, for the external force to be able to push the test charge against this field, The external force must have a magnitude that must amount to the electric force. The external force must have a magnitude that must amount to the electric force. And in this case, we say that the electric force, the magnitude of the electric force, is equal to the magnitude of the external force. Yes, the magnitude of the electric force must be equal to the magnitude of the external force before the test charge can be able to move against the field of this reference charge. And don't forget that we define the electric potential energy of a charge to be the work required or the work that must be done on the charge to bring the charge from infinity to a point Ra against an electric field. The electric potential energy of a charge is simply the work required or the work that must be done by an external force to bring the charge from infinity to a particular point Ra against an electric field. We said it is the work done. Yes, it is the work done because in the process of the external force working on the charge, the external force is storing a charge, is storing an energy in the test charge. And the energy stored in the test charge due to the external force is called the electric potential energy. And we said that before the test charge can move against the electric field, the external force must have a magnitude that must amount to the electric force. So now we want to look into the derivation of the magnitude of the electric potential energy. We want to derive the magnitude of electric potential energy. We know what the electric potential energy is now. The electric potential energy is the work that must be done by an external force on the test charge Q0 to bring the test charge Q0 from infinity to a particular point Ra against an electric field. It is the work that must be done on the charge. It is the work that must be done on the charge because in the process of the work done on the charge, energy is stored in the charge. Yes, energy is stored in the charge, and the energy stored in the charge is called the electric potential energy. So now let's look into the derivation of the magnitude of the electric potential energy of a charge. Now, we want to find the work that must be done on the test charge Q0 to bring the test charge Q0 from infinity to a point Ra against an electric field. We want to find the work that must be done because we said that the work that must be done on the charge to bring it from infinity to a point Ra against an electric field is the electric potential. So we need to find the work done, and once we are able to find the work done, then the work done will now stand as the electric potential energy of the charge. But don't forget that the work done is simply the force multiplied by the distance cos theta. Yeah, so now we want to find the work that is done from infinity to a point Ra, but we can't just find the work done straightforward because the path taken by the charge is not a linear path. The path is not a linear path, so we have to consider the tiny work done, the small work done on the path, and sum all the tiny work done together. The summing up of the tiny work done will give us the total work done on the charge from infinity to Ra. That is, we are going to find the small work done on the charge from a small distance. We call this the R because the total distance from here to here we can call it R. The total distance from here to here we can call it R, which we also call Ra. But now let's just call it R. So we are now going to consider the small part now, and the small part is called the R. The small part we are considering is called the R. We are going to calculate the work done from this small part, and the work done here is called the W. And the W now, which is the small work, will now be the force multiplied the small distance cos theta. Then from here to here also, we are going to find another small work done. Here we are going to, this is another small length, which you call, if this is the R1, this is the R2. So we are going to find the small work done. We are going to have another dW here. We are going to have another dW. We are going to be having small work done. We have to calculate the small work done, and the small work done is called dW. So summing up, the process of summing up the small work done, then it will give us the total work done from infinity to point RA. And the process of doing the summing up is what leads us to integration. We are going to do some integration in the process of finding the work done on the charge from infinity to a point RA against the electric field. So now we have that the small work done on this part, the small work done now is the W, which is equal to the force multiplied by the R, which is the small distance. The small work done is equal to the force multiplied by the small distance cos theta. Yes. So now, don't forget that the force we are considering here is the external force. We said the force here is the work done is the work done must be done by an external force. So the force here is an external force. So we can call this the W equals to Fx. That is external force multiplied by the small distance cos theta. But we said that the magnitude of the external force must amount to the magnitude of the electric force before the test charge can move against the electric field. So now this implies that the small work done is equal to the electric force multiplied by the small distance cos theta. Yes, we change the external force to electric force because they have equal magnitude. So now, what is our theta now? Theta is the angle between the small distance and the electric force. Theta is the angle between the small distance and the electric force. Don't forget that the direction of the direction in which the charge is moving is opposite to the direction of the electric force. They are opposite direction, and this implies that the angle between the electric force and the direction of the charge is 180. The angle between the electric force and the direction of the charge is 180. So here we have that theta equals 180 degree. So now we have that the small work done equals to the electric force multiplied by the small distance cos 180. Yes, and when you evaluate cos 180 on your calculator, this will give us minus 1. And now we have that the small work done equals to minus electric force multiplied by the small distance, which we call the R. So now, we now have to integrate both sides. That is, integrating both sides, we have this to be integral of the W equals to integral of minus electric force the R. So now when you integrate the W from your integration, you are going to add this to the W. And this will lead us to the negative. This is a constant. You can bring out the minus sign out of the integral. So this will have the negative integral of the electric force multiplied by the small distance. But don't forget that from the right, we are integrating the right from infinity to point R, to a point RA. Let's call it point RA in the field. So now, don't forget by Coulomb's law that our electric force by Coulomb's law is simply K multiplied by capital Q naught over R squared. So we can replace the value for this in this above equation. So this happens that the work done now is the negative integral of the electric force, which is this Q naught over R squared multiplied by the R. And don't forget, we are integrating from infinity to RA, because this is a definite integral. It is a definite integral. So now the expression here, we want to integrate this with respect to R. So we are to leave the variable of R alone. Every other alphabet or every other letter that is not of R will serve as a constant. So we are going to bring every other alphabet which is not R out of the integral to serve as a constant. So our work done is equal to negative K capital Q naught integral of 1 over R squared from infinity to RA dr. So now, when you integrate this with respect to R from your integral, we have that our work done is negative Q naught into brackets minus 1 over R from infinity to RA. Yes, we have integrated 1 over R squared. When you integrate 1 over R squared from your integration, we are going to have minus 1 over R. So now, when you multiply these two expressions together, we have this to be, this minus will cancel out this minus. Sorry, the bracket is supposed to extend up to here. Yes, this side is supposed to be. So now, when you multiply this negative sign with this, we have the work done to be equal to Q naught over R from infinity to RA. Yes, this is our work done, but we have to integrate it from the lower limit to the upper limit. So now this is how to do that. We are going to evaluate this expression at point RA minus the same expression at point infinity. So this will now be, the work done is now equal to Q naught over, anywhere you see R, we change it to RA. This is simply RA minus the same expression, which is Q naught over, anywhere you see R, we change it to infinity, and this is infinity. So finally, our work done finally will now be W equals to Q naught over RA, R subscript A minus. Don't forget that any number over infinity is practically zero. Not actually zero, but practically zero. So this expression is simply zero. Any number or anything over infinity is practically zero. So we have this to be zero. And finally, our work done on the charge from infinity to point RA is simply Q naught over RA. And don't forget that this is the work done on the charge from infinity to a point RA against an electric field. And we said that that definition is the electric potential. So finally, the electric potential, which we call U, is simply Q naught over R. You can just simply write it as R instead of writing RA. RA is the same thing as R, it's just that the RA is telling us about a specific point. So we can generalize it as R. And this is the magnitude. This is the magnitude of the electric potential is the magnitude of the electric potential energy of a charge. So here comes the end of the concept of electric potential energy of a charge. So in the next class, we'll be talking about the electric potential. Please don't forget to subscribe to my YouTube channel, and also don't forget to click on the notification bell to get notified whenever I drop a new video. My name is Moses Ola once again, and don't forget to share, like, and watch the video again and again. Thank you so much.